Good afternoon, candidates. Welcome to our chemistry lesson today. Yesterday, we were looking at reaction rates and reversible reactions. So we looked at some reaction rates. We started with defining what reaction rate means. Then we looked at theories of the reaction rate, where we said there are two theories, that is the collision theory and the activation energy theory. Then we looked at measuring how the rate of a chemical reaction is measured. We said it can be measured in 4 ways. Using the volume of a gas in unit time, change in mass of reactant products for solid products or reactants per unit time, then formation of a given mass of precipitate in a unit time, then a certain mass of reactants completely form products or diminish. Then from there we looked at factors influencing the rate of reaction. We said these are the factors that determine the rate of reaction. We talked of 5 factors. Do you remember the 5 factors? Name them. Good. So the 5 factors are concentration, pressure, temperature, surface area, and a catalyst. So we looked at how each and every factor affects the rate of reaction or influences the rate of reaction. So we started with concentration. We explained how concentration affects the rate of reaction, how pressure affects the rate of reaction, how temperature affects surface area. Then the last thing we looked at is how the presence of a catalyst, how a catalyst affects the rate of reaction. So on a catalyst, we said a catalyst only lowers the activation energy. So you remember we talked about activation energy yesterday, that minimum energy that the reactants should overcome for them to form products. So what a catalyst does, we say that it lowers the activation energy. When it lowers the activation energy, the chemical process speeds up. So meaning it increases the rate of reaction. So the time taken for the reaction will be shorter. So we said a catalyst is a substance that just speeds up the rate of reaction, and we say it speeds up the rate of reaction by lowering the activation energy. So we say that there are some biological catalysts, the one you studied in biology. There's some catalysts that are formed by themselves. They are altered physically, e.g. from solid to powder to fine powder. So those are catalysts. There's some and we say that this activation energy is lowered in different ways. So they're lowered by forming short-lived immediate compounds called the activated complex that break up to form the final products. It's also lowered by being absorbed by the reactants, thus providing the surface area on which the reaction occurs. So a catalyst has no effect on enthalpy of reaction, but only lowers the enthalpy of activation, or what you call the enthalpy of activation, what you call the activation energy. So that it's also called the activation energy. It does not affect the influence where the reaction is exothermic or endothermic. So we looked at this energy level diagram, and we say that if a catalyst is not used, so the rate of reaction, like between the compounds A and B it will start by breaking the bonds. So there will be some energy that supposed to be used to break the bonds. That's what you call the activation energy. So a lot of energy will be used to break these bonds, then up to there. But if a catalyst is used, the energy used to break the bond will be lowered. So that energy will be lowered. So meaning the breaking the bonds will be easily will be made easy. So the products will be formed more easily. So when you draw a graph, the one with the catalyst, the part of activation energy will be lower. So this blue line will show what? The one with the catalyst, and the black one without the catalyst. Without the catalyst. So from there, let's look at some catalyzed reaction processes. Some catalyzed reaction processes you have learned. So from Form 1, Form 2, Form 3, up to Form 4 now, you have learned some processes that requires a catalyst. So many of them. So can you remember some of them? So mention a few. Mention a few. Okay, good. So hope you have mentioned some of them. So let's look at just some of them. There are so many. Let's look at some of them. So the first one, you remember when you were in Form 3, we were looking at large-scale manufacture of sulfur 4 oxide. You looked at a process called the conduct process. So you are using sulfur 4 oxide with some oxygen to form sulfuric 6 acid when it's diluted with water in a form sulfuric 6 acid. So the process of changing sulfur 4 oxide to sulfur 6 oxide, adding more oxygen to sulfur 4 oxide to make it sulfur 6 oxide requires a catalyst. And during that time we say that we use a catalyst called vanadium 5 oxide. The most preferred catalyst is vanadium 5 oxide. We said also platinum can also be used, but the one commonly used is vanadium 5 oxide. So vanadium 5 oxide catalyst oxidizes sulfur 4 oxide to form sulfur 6 oxide during the large-scale manufacture of sulfuric 6 oxide. And we say that we normally use vanadium 5 oxide for two reasons. One, we said it's cheap, and two, we said that it does not poison it does not contain any impurity, thus it's less poisoned. It's is not easily poisoned. It's not easily poisoned. Then from there, just back before the conduct process, there's another process you looked at, the Ostwald's process. Do you remember the process? What do we prepare in Ostwald's process? Good. So in Ostwald process, we prepare nitric 5 acid, the large scale manufacture of nitric 5 acid. And you remember that process when we were adding oxygen, we are oxidizing ammonia to give nitrogen 4 oxide. We use a catalyst. Which catalyst? Name the catalyst. Yes, good. So platinum rhodium catalyst is used. Platinum rhodium catalyst is used in this process, and we clearly say that during that process, the platinum rhodium should be in powder form. So it should be crushed to be fine. So the particles of platinum rhodium should be fine for them to be effective. So meaning we are increasing the surface area. You remember what we said yesterday, the impact of increasing the surface area on the rate of reaction. So we are using this platinum rhodium that is that is in powder form for us to do what? To increase the surface area, thus increasing the rate of reaction. So in platinum rhodium is used in oxidation of ammonia to nitrogen 2 oxide and water during the manufacture of nitric 5 acid. Then before the Ostward's process, we looked at the Haber process, the manufacture of ammonia. We also use a catalyst. We said in the Haber process, we always use platinum or iron catalyst. We normally use iron catalyst to combine nitrogen and hydrogen to form ammonia. So for nitrogen and hydrogen to be combined to form ammonia, an iron catalyst should be used. Also, in the same class in organic chemistry, when you are looking at hydrogenation, what you call hydrogenation. What is hydrogenation, candidates? Hydrogenation? Good. So we said hydrogenation is addition of hydrogen on the organic compounds, either the unsaturated compound, the addition of hydrogen. So when hydrogen is added to unsaturated compound, it gives you a saturated compound and another compound, what you call in a process called what you call hydrogenation, and that process requires a catalyst, and the catalyst used there is what you call the nickel catalyst. So the nickel catalyst, the one that speeds up that type of reaction, what you call the hydrogenation. Then another one, we also looked at the composition of hydrogen peroxide. That is now in Form 1, when we were preparing oxygen. We said oxygen can also be prepared by decomposing hydrogen peroxide. So when you decompose hydrogen peroxide, you get oxygen as one of the products and water. And in that process, there's a catalyst we use. Which catalyst, candidates? Oh, good. So you remember Form 1 work. We say that during laboratory preparation of oxygen, we can use this method of decomposing hydrogen peroxide. Hope you remember 3 methods of preparing oxygen that you learned in Form 1. So this one is just one of them. Decomposition of hydrogen peroxide, and we always use manganese 4 oxide as a catalyst. Manganese 4 oxide as a catalyst. So when hydrogen peroxide is decomposed to give oxygen and water, the manganese oxide there is what it acts as a catalyst. It speeds up the rate of reaction. Then the process is a reaction of metals with dilute acids. Here, you remember when we were preparing hydrogen gas, that is Form 1 work. Hydrogen, water, and hydrogen. When we were preparing hydrogen, we remember we said that hydrogen gas can be prepared by reacting a metal and a dilute acid. A metal and a dilute acid. And we say that preferably zinc metal is used. Magnesium metal can also be used. We say the reason why it's not commonly used. Do you know? Do you remember that? We also say that potassium, sodium, and calcium cannot be used to prepare a hydrogen gas with a dilute acid. Copper, iron, and gold also cannot be used. What's the reason behind that? We also say that an acid like nitric 5 acid cannot be used. It cannot be used. What's the reason? Then we say that calcium is not also used with what? With sulfuric 6 acid. And we gave a reason why we cannot use calcium metal with sulfuric 6 acid when preparing the acid. Then we came up with the most preferable acid, hydrochloric acid, or you can as well use use sulfuric 6 acid with zinc metal. Then in that process is just reacting this acid, the mineral acid Ni, with zinc to give you the salt, that's a chloride. Then the zinc chloride or zinc sulfate if you are using sulfuric 6 acid, and hydrogen gas. So we said, but in that process calcium sulfate should also be there. So this calcium sulfate is there, is not involved in the reaction, is not changed. We said it is used as a catalyst. Calcium sulfate is used as not calcium sulfate, but copper 2 sulfate. Copper 2 sulfate is used as a catalyst. So it speeds up the rate of reaction, that's producing enough hydrogen gas. Then some other catalyst reactions such as substitution reactions in organic chemistry. When placed in bright sunlight of UV and ultraviolet light, a mixture of halogen and an alkane undergoes substitution reactions explosively to form halogenoalkanes. You remember, when placed in diffuse sunlight, the reaction is very slow. So it needs sunlight for it to make a lot of haloalkane. Then in photosynthesis in biology, you learn how plants convert carbon 4 oxide gas from atmosphere and water to form glucose and oxygen. So plants are using carbon 4 oxide and water to form glucose and oxygen. And your biology teacher told you that this process cannot take place if sunlight is not there. So in absence of sunlight, no photosynthesis. But in the whole process is only carbon 4 oxide and water that is being converted to glucose and oxygen, which are the final products of photosynthesis. So meaning this sunlight is there just to speed up the rate of reaction. For carbon 4 oxide and water to be converted to glucose and oxygen, sunlight must be there. Just to do what? To make the process occur. It's not involved in the process, does not affect the products formed, does not affect the reactants, but it only speeds up the rate of reaction. You remember your biology teacher teaching you the conditions necessary for photosynthesis to take place. So sunlight must be there, but it's not one of the raw materials. So raw materials of photosynthesis, carbon 4 oxide and water, but the conditions necessary for photosynthesis. Now we talk of sunlight, a catalyst. That sunlight is a catalyst. Then in photography, in photography also sunlight is used as a catalyst in photographic films, which contain the silver bromide emulsion that it decomposes silver and bromine, so it should be exposed to sunlight for them to decompose those products. Okay, so those are some of the catalyst reactions. So in our next session, we shall look at some questions concerning this topic. Then we introduce another part of this topic, the chemical equilibrium. Bye.